Good afternoon, everyone. This is Shravani from WRI. I hope you all are really keeping yourselves safe and maintaining social distance and keeping yourself busy doing whatever you like. I'm really glad to see such a great participation level in spite of such difficult times. So, but in these are the times where technology comes in hand, and thanks to the technology that we are still connected wherever we are, no matter how far or near we are, and the sharing of knowledge never stops. So I welcome you all to this new month, new topic in our webinar series. So when I talk about the webinar series, I'd like to give a little bit of introduction before we start off. I see most of the people here are regular attendees. However, I see a lot of new faces as well, which is great. So yeah, I mean, I'll give you a brief about what is it and how did we start these webinar series. So this is a part of the project called the Electric Mobility Forum, which was launched by the Vice President of India last year. So when we came up with this project, we had in mind that, okay, a lot of people are working towards EVs. However, there is not a common platform where people can exchange and share and gather knowledge, in a single platform, because everybody is working in their respective domains, in their expert areas. However, people just don't know about each other. So we came up with 3 simple techniques in order to accelerate electric mobility's adoption in the respective states and cities in India. So one was convenings, which means that we do a lot of thematic and focused state and national level workshops, roundtables, and conferences where we meet people, which gives a lot of chance for talking one-on-one and exchanging our resources. Second is the scaling part, which is now very useful in times such as this, which means it is a technological platform where we can exchange knowledge. This could be in the form of webinars, which we always do. And we also have a monthly newsletter called the EV Connect. Do check it out if you haven't already yet. And there are different kinds of articles and blogs and papers that we do. And the third one is on mentoring. That means hand-holding with the state governments in order to accelerate the adoption of electric mobility with whatever technical guidance that we can provide them, in our assistantship. So so far we have completed many of such webinars in the webinar series, which were really EV related. So one thing that you can see is that all the topics here related to EVs, of course, are very India specific. I know it is great to learn from Western countries because they are super successful. However, India has its own challenges and problems. So it is important that people might want to know about custom made or homemade solutions, which is implementable. Because imagine if we go from one city to other or one state to another, there are huge differences in terms of institutional, topographical, climatic, or just name it and we have it. So it's so diverse. So how do we make all these ideas or possibilities feasible, scalable, and economically viable? One key difference that I have experienced from past year, from this to this year, is that last year we were talking a lot about EVs in the stage where we were still thinking of doing it. If this would happen, then how would be the challenges? But now from January onwards, I can see that a lot of our topics are very real life problem centric, which means that people have actually started working on ground and they have started coming up with their actual experiences and challenges, which is amazing. And this also brings us to the topic for today, which means that along with EVs, now there are a lot of talks around different kinds of types of technologies, new kinds of technologies. So we were just curious to know, yeah, people are just talking about it and assuming things because obviously there isn't much information in the internet, and even if there is, it's sometimes a waste of cyberspace because so much information confuses us. So that brings us to the topic for today, which means that what are these kind of disruptive technologies available in India, or just we talking about it and panicking a lot. So with you have already registered for it, but reading it out again, so which means disruptive potential of fuel cell technology in the Indian transportation sector. Now, if I have to define what is the disruptive technology, it means that a technology is the one that displaces the established technology and shakes up the industry, or a groundbreaking product that creates a completely new industry. So people are kind of worried. So we have a lot of participants from the manufacturer side and the investors. So they're kind of freaking out, like, oh my God, we've spent so much money in the EVs. What if this new form of technology comes in and then, like sways away everything? We're going to get bankrupt, right? So are these like really myths, or are these, like really factual? So we're going to find out all of these today. So to throw this light, not many people in India really know about all these kind of technologies. So we were really, really lucky to catch hold of the speaker for today, which is Dr. Prakash Chandra Ghosh. He is a brilliant person, and he's been working all throughout in these kinds of new forms of technology. And currently he is a professor in the Department of Energy Science and Engineering in IIT Bombay. So people from abroad, like our international attendees, those of you don't know what is IIT, it is Indian Institute of Technology. It's supposed to be one of the top institutes for research and development, and also all kinds of, like engineering and innovation related studies. So it's a great institute. So a brief about Dr. Ghosh. I'm sure he'll be giving an introduction about himself as well, and I wouldn't be doing much justice by giving it. However, a little bit about him. So Dr. Ghosh received his doctoral degree in mechanical engineering from RWTH in Germany, and he's also a recipient of the Boycast Fellowship from DST, Government of India, and Erasmus Mundus Fellowship from European Union. And he has worked extensively in Germany and also in the National Chemical Laboratory in Pune as a scientist from 2004 to 2006. He has a lot of interest in very exciting topics such as low temperature fuel cells, which include designing, modeling, and fabrication aspects. He has written more than, can you imagine, like 50 international journals in the field of solar energy, fuel cells, hydrogen, etc. And there's a lot more, but then summing up, currently he is also, leading the project, which is funded by the DST, Department of Science and Technology, Government of India. So yeah, I would leave it on this, and then I'll be telling you what are the kind of things that he's going to cover in today's topic. Number one is, what is the current status of understanding of fuel cell technologies for transport sector in India? Mind you, again, these topics are very India specific. What are the fuel options for fuel cell vehicles in India? What are the potential challenges of hydrogen and fuel cell technologies? It's techno-economic challenges for commercialization in terms of like if we have to make it scalable and feasible in India. And also, what are the potential of early adoption of fuel cell technologies in different vehicular segments of India, right? So without taking much time, I end up over here giving you the most boring part of the webinar, which means the logistical part. So I have received a lot of questions from you guys, and thank you for them. So I've clubbed in together and tried to, fit into different questions, which might, if we have time, then we'll take most of it. But however, again, apologies in the beginning that if we don't have much time, I'll, however, try to address as much as I can because, again, of time constraints. But in the process of attending the webinar, you might have a lot of questions in between. So I would request you to please send out your questions in the questions box and not in the chat box. So when you send out your questions in the questions box, I can see your name, designation, and organization. So whenever, in case we fail to answer your questions right now, we can always take it up from him later on, and this will be uploaded in the same link as you have registered for as a public query. Number two is, if you are busy taking notes or photographs, or you are worried that your internet connectivity is miserable and you've missed out on something, don't worry about it, because we have the whole video recorded, and in a week or two, We'll be uploading the video and of course the presentation of the same in the same link that you have registered for. So yeah, that brings the end of my introduction, and I will hand it over to Professor Kosh, and in the end we'll take up the question answers round. So I hope you do enjoy this topic. It's quite a new and exciting topic, and make the most out of it. So over to you, Professor Kosh. I'll be making you the presenter now. Yeah.
Thank you, Shravani. So I'm audible, right?
Yes, sir, you are.
Okay, thank you, Shravani, for the nice introduction. I don't need any more introduction, so I can directly jump into the topic. Good afternoon, everybody. So myself, Prakash Ghosh, I'm from IIT Bombay. So, and I would like to thank WRI-India also for giving me this opportunity and also sharing my views on fuel cell and also its potential in Indian sector, Indian automobile sector. So let me directly go to the slides. So today's topic that is being decided is that disruptive potential of fuel cell technology in the Indian transport sector. So let me use my pointer. Okay, so now it's visible, right? Pointer is visible.
Yes, it is visible.
Okay, all right. So good afternoon once again, everybody. So myself, Prakash Ghosh, I'm going to talk on fuel cell technology in the Indian transport sector and its disruptive potential. So the outline for today's presentation as follows. I'll be giving a general introduction on fuel cell and also its need for it. And when we are talking about fuel cell, of course, we cannot avoid IC engine or the conventional technology what is there, or also intermediate technology that is coming like an battery-based electric vehicle. So we'll be having some comparison mainly with the IC engine and why fuel cell is so important. Then we'll talk about different types of fuel cell technologies, and then what are the fueling options for fuel cells, and what are the main challenges for fuel cell, that is why it's not coming in the market, and finally we'll talk about conclusions. Before going to the topic, let me give some introduction about the place where I come from and also about my department. So there are total 23 institutes. It's known as Indian Institute of Technology, and one of them is Indian Institute of Technology Bombay. So it's B for Bombay, not Mumbai. So it's a IIT Bombay in Mumbai. You can see here. My department is Department of Energy Science and Engineering Department. It is fairly new department in India, in IIT Bombay. It involves in energy related teaching and research, and we have total 23 faculties and more than 400 students. And we mainly offer dual degree, that's a BTech MTech degree and MSc PhD degree. Along with that, we offer MTech and PhD degree. That's all about my department. Let me come back to the topic. So the general introduction, if you are talking about, so this particular slide represents the future generation. And the need of the future generation is that clean environment and clean water. These are the one or two of the important parameters that we have to take care of. And that can be taken care by the energy, and that's the energy demand. That's all, if we can mainly take care of that. Now, if you are talking about energy demand at present, it is being taken care by the fossil fuel. And then all of us, we know the threats and consequences of the fossil fuel. So there are two types of the threats. One is we call the threat on the fossil fuel by mankind, and the consequences of that we talk about is that the reserve fossil fuel is limited, and the depletion of fossil fuel is going to happen. And these are all these things we know. Now, and as a result of that, coal will be depleted in 300 years. Petroleum is going to be depleted in 40 years. We are not going to debate on this number 340. These are always evergreen number, looks like to me. But by this number, we never try to talk about the 300 years. We try to talk about future energy crisis. It can happen in 300 or 1000 years, but it doesn't matter if you take the total, the time of the human history, then 300 and 1000 years is same. So this is the one side of the coin, and that's a threat. And if we think that this is the reason why we need to have some alternative solution, it's not right. And here I remember the very famous quote, which was given by Don Howard from, and is that the Stone Age did not end because we ran out of the stone, and the oil age also will not end because we run out of oil. So the driving force is different. So that's the reason. One of that is that we want to get rid of the global warming problem, and fuel cell is that one of the component or contender which is being believed that it can also help. So what is a fuel cell? Fuel cell is an electrochemical device which converts chemical energy directly to electrochemical energy. It has some salient feature like it's a higher efficiency, higher lifetime, no moving parts, extremely quiet in operation, and less emissions. Now, if we are also only looking into the higher efficiency point of view now, so to understand that how it helps in case of global warming problem, so let us take an efficiency and business as usual scenario. So where we are burning coal and then in thermal power plant, and then we get 25% efficiency, that means electricity, and 75% wastage of heat. And then if you are transmitting, finally you are going to get in the range of 19% of electricity. This is an Indian context where we have the transmission loss is also very high. And then after that, this particular energy which is being transmitted from the thermal power plant is being used for fan or light. But when it is used for heating the water, then I feel it's a crime, because already we have wasted 75% of the energy as a heat, and then again we are using this particular energy for heating the water. What could be the non-conventional practice and how we can improve the efficiencies? So if we take, let's say, normal LPG gas, and then you have a burner and directly you try to heat, and you will be able to get and achieve a 65% efficiency compared to the 19% efficiency, which helps actually giving the life what I was talking earlier, 300 years, that can go immediately three-folds to goes to 900 years. So that's how that if you are also taking some of the appliances which is efficient, it also increase the lifetime of the reserved fossil fuel, so that the scientists have some time to think, and then we can have an alternative solutions. So now if you take the efficiency comparison in the conventional system, like at present what we have, so you take fossil fuel, then it's being combustion, then mechanical, then electrical, then electricity. Now the characteristics of this particular system is it's emits direct greenhouse gas, it's a high temperature operation, so you'll be having NOx and others pollution as well. It's a lower efficiency, and even if you are operating at a partial load, it even gives you worse efficiency, even lower than that. And it's loud operation. The good part of it, it is having low investment cost, as well as it's having it's an well established technology. Compared to that, if you go for fuel cell based technology, so it's a indirect or lower emission compared to that, as it's having higher efficiency. It's also the good part of this is that if you are operating fuel cell at partial load, even you get more efficiency compared to the rated power. So this particular thing, when you are talking about, it makes because of this, fuel cell becomes very attractive compared to the conventional system. Like if you are going for a city where you will be operating always in the partial load, you will be getting much higher efficiency. But in conventional system, always we know that if you are going in a city type of system where your vehicle is running in a partial load, and you will be having lower mileage. And the other interesting part of this, it's a quiet in operation. The bad part of this, it's actually still in R&D, and it's having high investment cost at present. Now, also I wanted to share one more thing. When we talk about efficiency of the conventional system as well as the fuel cell based system, so I will be taking a ballpark number. Like in case of fuel cell, we tell 45 to 50% efficiency what we have achieved. And compared to the conventional system, when you are talking about, let's say 30%, so there are people, they can argue that it's only 15%, not a big deal in this. One thing we should remember, in case of conventional system, when you are talking on efficiency, it is the highest achievable efficiency. When you are talking about the fuel cell, it is the lowest efficiency that what we can get, and at partial load it will be going. So this is actually the two extreme boundary of the band that we are talking about in the efficiency range. In one case it is the minimum, other case it's the maximum. So always it's not good to compare the efficiencies directly when you are talking about fuel cell and a conventional system. Then the efficiency comparison, if we do here, it is the temperature is being plotted with efficiency, and this is the fuel cell efficiency. Or you can see that with the increase in temperature, fuel cell efficiency comes down. With the increase in the efficiency, the Carnot efficiency increases, and something it looks like that. So, but you can see that at low temperature region, you will be having much higher efficiency compared to the Carnot efficiency. And ideally, you'll be getting at standard condition around 83% efficiency, where it's shown here. How fuel cell looks like and how it is different. So and also from this in next few slides, I'll try to configure or construct the fuel cell from an IC engine point of view. So let's say in case of fuel cell, fuel and oxidant is being given. Like in case of, also we are taking now like a conventional IC engine chamber where you are giving fuel and oxidant together, and as soon as you are giving there, so their combustion will take place, and as a result of that combustion means the fuel will be oxidized and oxygen is going to get reduced, and finally you will be getting combustion taking place. And if you see very carefully, you will be able to know that oxidation and reduction means there is an electron transition is taking place there, and so then we are going to get heat. Now in case of, also we know that electricity is also that nothing but the amount of electron that is flowing through the external circuit per unit time. So now what we are seeing here, that electron that is going from let's say fuel to oxidant, and then we are getting oxidation and reduction. Somehow if you can arrange this electron mixing, and then we can get this electron through our external circuit. So instead of getting heat and light, we can get electricity. So that means when we are converting the chemical energy, we can get either from chemical to heat energy, or we can avoid heat and we can get directly electricity. How can you do this? So for doing this, the first thing what you need to do, we need to arrest this electron that is going from hydrogen to oxygen, and that's and also oxidation and reduction that is happening there. So for that, what you have to do, first you try to take a membrane like this, which arrests this electron movement from hydrogen to oxygen. So instead of having one chamber, what was having in the combustion chamber, now we have made two chambers, and we tell in one chamber to other chamber electron cannot go through this particular separator, but this separator will be good for making the charge neutrality. So it will be allowing ion to move, and then electron, what will be happening with the electron? So this is that small place what we are telling, this is the separator what I have, and now this fuel will be coming here and it will be going through the external circuit, and then you will be getting electricity produced, and then other side electron will be coming through this, your ion will be coming, and then they will be combining together with oxygen, and you will be getting the same reaction what we are talking about combustion. But now in this case it is a controlled electron movement, so you can get electricity instead of getting heat and light. So that's what now you can understand that you will be having two chambers separated by a separator, and then you will be having a site there that oxidation can take place. So if you go to the basic configuration of fuel cell, how it looks like. So you will be having electrolyte. We call this an electrolyte. This is earlier I was talking about a separator which separates both the chambers. Then you will be having a catalyst layer. Here you will be having one catalyst layer. This is other, we call it an electrode. Then you will be having a gas diffusion layer. We call it also support layer, which gives support to the catalyst layer. And then finally you will be having the flow field through which gas will be passing through the fuel cell. And then this side, one side you call it as an anode, other side you will be calling it as cathode. Now, if you can see here that when we are talking about the dimension, I wanted to also mention about here. So if we talk about electrolyte, typical dimension in case of fuel cell will be in the range of 100 micron, so which is like a normal A4 size paper thickness. Then the electrode will be in the range of 15 to 20 micron. After that, the gas diffusion layer will be in the range of 0.3 millimeter, that means around 300 micron. And then if you see this flow field design, that flow field will be in the range of 3 mm. So I was trying to tell you that you can see the increase in the dimension is in the order of magnitude 10 almost. And the actual reaction that the powerhouse is, you can say that electrolyte and that electrode, which is hardly 100 micron. Why I'm telling these things, because in next few slides we'll be talking about the volume and space and weight that is required for the transport sector and who is contributing to that, and really what is the contribution, how much, that's what we are going to discuss in next few slides. And then here when we are giving fuel goes like this, oxidant goes like this, and then fuel diffuses through the gas diffusion layer, and similarly oxidant diffuses through the gas diffusion layer, and finally we get the ball. What are the types of fuel cells? So now there are different types of fuel cells available in the market, like polymer electrolyte fuel cell. This is one where hydrogen is being used, and H+ ion goes through the electrolyte, and through external circuit you'll be getting the electron coming out and then giving power, electricity, and then you will be using oxygen here, and you'll be getting water as a byproduct. Similarly, the other one, we call it as a direct methanol fuel cell, where methanol is used as a fuel instead of hydrogen, and the rest of the things are similar like fuel cell. And then operating temperature, you can see here it increases. So slowly we can go off, and the temperature also increases, and different types of fuel cell comes. This is an alkaline fuel cell. I don't have time because we want to go for other things we want to discuss. So I'm a little bit going fast here. I'm not discussing too much here. And these are mainly I'm discussing this because thinking in a wide audience, probably some of the people will not be having any idea about fuel cell. And I'm sorry if those people have idea about it, because we'll be discussing in my next part where it will be interesting for you people. The next one is the molten carbonate fuel cell, and the operating temperature is 650 degrees centigrade, and then other one is that solid oxide fuel cell, which is 750 to 900 degrees centigrade. You can see here that the temperature is increasing from 60 odd, you can tell me, room temperature to 900 or 1000 degrees centigrade. So based on this, for the different types of application, different types of different types of fuel cells are being used. And for automobile sector, polymer electrolyte fuel cell is considered to be the main contender, and it is being explored. So this is the other way. I'm going very fast in this slide. So these are even the naming of the fuel cell is very interesting. Sometimes the names are being based on the electrolyte, what I was telling in the middle as a separator. So you can see here alkaline, polymer, phosphoric acid, molten carbonate, solid oxide fuel cell. These are the mainly based on the electrolyte name. And for also when you are using the fuel, based on the fuel, also some of the fuel cells names are there, like direct alcohol fuel cell, direct methanol, direct ethanol, direct borohydride, direct carbon fuel cell, direct formic acid, and microfuel fuel cell. These are based on the fuel that is being used. Now we are just now concentrating slowly on the fuel cell that is important for the automobile sector. This is a polymer electrolyte fuel cell. So in this type of fuel cell, mainly hydrogen is being given, and it is oxidized on the anode, and then electron goes through the external circuit, and as well as the H+ ion goes through the electrolyte and goes to the cathode side, and on the cathode side it combines with the electron and also oxygen, and it produces the water. So this is how the electricity is being produced in fuel cell using the oxidation tendency of the fuel, mainly hydrogen. Now the thermodynamics of the fuel cell a little bit. So this is if we talk about the fuel cell voltage, how much you are going to get per cell, you will be getting that we can always calculate from the Gibbs free energy divided by the total Faraday number, and that number comes in the range of 1.23 volt per cell. This is very important because when you are thinking about the stack and other things, so why we need a stack, multiple cell stack, to understand that. So this is we can get from this for the delta G value for hydrogen and oxygen giving water is 237, and if you divide by the N is equal to 2 and F is equal to 96485, you'll be getting 1.23 volt per cell. And then, but this is an open circuit voltage. If you are going for the operation, then you'll be having the Also you have to accept the losses. So there are different types of losses we call, sometimes overpotential loss, polarization loss. These are the different names, and these are the different types of losses: activation loss, ohmic loss, and concentration loss mainly. And these are the equations. We are not going in the detail of the equation, but we can go by the trend. So activation losses looks like this, and ohmic loss is linear. It follows Ohm's law, and this is the mass transfer loss or concentration loss. It is dominant in this zone for the current. And if you combine all these losses, the loss looks like this. So you'll be having an activation losses zone, ohmic zone, and then dominated, and then this zone, and then finally the characteristic curve of IV characteristic curve of a fuel cell looks like this. So if you are increasing the current, you'll be getting a voltage like this. And the typical curve, if you see here, it looks like this. This is a typical 5 kilowatt cell stack. X-axis, it is the current density. That means the total current divided by the area of the electrode. And the voltage, you can see, I told 1.23 is a theoretical voltage what you can get, but if you are using air, you'll be getting in the range of 970 millivolt per cell. On the y-axis, what is being plotted is that power density. What you can see that maximum we can get with this cell, even you can get better than this. It is 0.5 watt per centimeter square. This number, I do not know whether you can understand whether it's a very small or very big. It's a really very big number. Because let us take an example of an A4 size paper. I have made an electrode fuel cell of electrode area of an A4 size, which can give you approximately 600 centimeters per area. And if I use that type of electrode, from this power I can get that I'll be getting in the range of 300 watt, because 600 into 0.5 watt per centimeter square is going to be 300. So from a single cell I can get now. Earlier I told my membrane thickness is also like an A4 size page thickness. So you can think that you have a membrane of like thickness of a A4 size, and you can get 300 watt out of it. If you are attaching two electrodes on both the sides, is hardly 15 micron. So, and then if you use like this you'll be getting 1 kilowatt. So that's why it's really very having very high power density. If you are talking about the, that's why it's so attractive for transport application. What are the components we have? So we have electrolyte, electrode, supporting layer, bipolar. So you can see here, this is the membrane or electrolyte, what we call about. The next one, this is the electrode. These are the gaskets. These are the gas diffusion layer. These are the bipolar plate, and this is the end plate. And finally, we can tighten it using our ports. Now, electrode, what is there? When you are talking about this particular reaction, hydrogen is getting oxidized and becoming H plus ion and electron on the anode side, and cathode side, oxygen is getting reduced with H plus ion and electron and giving you water. You need, and if you want to perform this at room temperature or very low temperature, you need precious metal catalyst like platinum. And so it looks like this, but platinum you need very small size. So generally 2 to 3 nanometer, that's the platinum size, but that is being actually structured and designed on a carbon which is having a size of 20 to 40 nano. So here you can see carbon, and these are the platinum. And then you will be having a porous carbon electrode what is being made. Because why need porous? Because through the pores gas can go and then it can react on the platinum surface. And this is one of the people believe this is one of the main culprit why fuel cell is not coming in the market. And then the morphology, if you see, this is your electrolyte, and this is your electrode where gray color is your catalyst and white color is your carbon. And then you have also a noodle type of design which connects all the platinum to the electrode, so that H plus ion can move through this electrolyte and goes to the other side. So this is the electrode morphology. Then next one, as I was telling, after electrode, you will be having a important component is that the bipolar plate. So the role of bipolar plate is to distribute the gases. So you'll be having a channels through it the gas is getting distributed, and this particular plate is having a thickness of 3 mm, and so that's why you can see that now entire volume is going to, and weight is going to come mainly from this particular component. So if you are thinking about automobile sector and you want to do some R&D, you need to work on this. And at present, people try to use graphite based. That's why you need very thick plate. These are some of the conventionally used flow fit. And if you are giving gases, you'll be having a pressure drop, and which creates a non-uniformity if you are making a scale-up system when you are going for an automobile sector from the lab scale. If you see that unit cell, this is another way of looking at it. So this is your membrane electrode assembly. It is known as MEA. Then it's your backing layer or diffusion layer. Then it's your gasket. Then it's your bipolar plate. Then from both sides, you will be making an end plate, and your single cell assembly is ready, which will be able to give you a voltage of 0.5 or 0.6 volt. And these are the inlets. What you are talking about: fuel inlet, fuel outlet, oxygen inlet, outlet, and you will be also having a coolant inlet and coolant outlet. And then this is a unit cell assembly. Now, if you want to make multiple cells and you want to have, then you need to put them in series. So, but this is not a right way of doing a series. So, if you are doing a series connection, you can put one after another. So, you can stack this, and then we call it a fuel cell stack. So, anode cathodes are there combinedly, and this is how it looks like. When you have a multiple cell stack, it looks like you are putting multiple cells together and you are stacking, and you are reaching to a desired level of voltage and also a desired level of current you get from the electrode area. So this is how a fuel cell looks like. Now, where from, if you are talking about fuel, where from this fuel, what are the fuels it can accept, and where from this fuel is going to come. So now there are three different ways that we can get fuel. One is that from fossil fuel, other one is that from nuclear energy, and third one is from renewable energy. Now, if you are talking about fossil fuel, this is a conventional way of producing hydrogen, where coal or oil or natural gas is being used. And in case of renewable, you can use all solar thermal, solar photovoltaics, wind or biomass, and you can also get the hydrogen. Now, in case of fossil fuel, this is the chemical energy, and then you can use reforming. I'm not going in more detail of this, and from through reforming you can get hydrogen. But there is an important thing that after reforming you can also get carbon monoxide, which is very much poisonous for the catalyst that is being used in fuel cell. Now, so for the low temperature fuel cell or PEM fuel cell, what we are talking about, it can take up to 25 ppm of platinum. Beyond that, even 15 to 25 ppm, which means that you need to, after reforming, you need to clean the fuel thoroughly, and which involves lots of cost. So other one is that nuclear energy or solar thermal, where you can concentrate with a higher concentration, and you can use that thermal energy, and you can do use that thermal energy and directly you do thermolysis of water instead of electrolysis, and you can get water produced, hydrogen and oxygen produced, and that's the other option. And it can be also, it is also thought that this would be one of the sustainable backbone for the hydrogen economy. Next one is that if you are using solar photovoltaics and wind, and you can directly get the electricity, and you can use in the electrolysis process. So you call, sometimes it's a solar hydrogen or renewable hydrogen, and you can get this. This is the advantage of this. You will not be having any poisonous like carbon monoxide in it, so you can directly use in fuel cell without any problem. And also in case of biomass, the same thing, like you are using natural gas, another thing you can get from biomass as well, and then you can do reforming and can get hydrogen. After that, you get this hydrogen, you need to store that hydrogen, and there are different options available for it. You can also do this reforming on board sometimes, but instead of doing on board reforming, it's good to do reforming centrally and then store it in on board. That will be much better option. So one of the options for this is that it's known as, it's a chemical absorption, and then it is mainly in the MOFs. But the temperature you can see -196 degrees centigrade, which is very low temperature version, but you will be getting very high storage capacity. Now, if you go for next one is the catalyst bed, where you can have chemical hydrides and you can get also catalyst. But for this, when you want to dissolve it, you will need some catalyst. Other one is that liquefaction. Directly you can liquefy hydrogen at -253 degrees centigrade, and you can get very high energy density, but it's also energy intensive. Fourth one is that you can have also metal hydride, and then with that metal hydride you can also get hydrogen, and it can be also do, and this is conventionally now at present people are practicing this one, where you can store up to 700 bar bottle and compressed, and where you will be getting up to 50 kg per meter cube, which is reasonably also very high. So these are the different options of storing hydrogen on board, and mostly the promising options for automobile sector is this one, compressed hydrogen or the metal hydride. And then finally it can be used in fuel cell. Now what are the targets if we are talking about the hydrogen storage, which is given by DOE, and then this is the target, that gravimetric capacity, that's in weight percent. This is sometimes people confuses, this is not the only the materials, it is the system capacity. That means your material plus the system balance of plant. That system capacity, gravimetric capacity should be 4.5, 5.5 and ultimately 6.5. System volumetric capacity, it is 30, 40 and 50. Now I wanted to give an idea that if you are storing hydrogen at 700 bar, so volumetric capacity becomes 62.5. And then refueling time should be 3 to 5 minutes. This is one of the major bottleneck if you are going for the metal hydride and other storage. But for high pressure tank, this is the advantage because you can easily store in 700 to 700 bar within 3 to 5 minutes. And the total life is expected 500 cycles. That is up to depth of 75%. Depth of discharge is something like battery. That means if you are emptying 3/4 of the storage. If you go for fuel cell stack, this is the target what is being given, and like power density 300 or 3 kilowatt per liter, and also 2 kilowatt per kg is the specific power. Cost is 53. These are the 3 points which is very much crucial for automobile sector. Efficiency people have achieved in the range of 60% or 55-60% people have achieved. So this is not. So these are the major challenges what is there. And also durability 3,900 and ultimately 5,000, 8,000. Even if I'm talking about 5,000 an Indian context, if I tell that I'm going to sell a car which is having a life of 5,000, that fuel cell is having, that means your engine is having 5,000. It sounds that's having very less. 5,000 will not be appreciating at all. But if we talk in terms of kilometer, taking an average speed of let's say 20 kilometers per hour or 25 kilometers per hour, that gives us actually 1,25,000 kilometers, which is for Indian road even more than enough. Even my car I'm driving for last 15 years, still I have not crossed 70,000 kilometers. So that's why this number, though it looks very small, but it's a good number for automobiles. And if you go for system level, the one that what I was talking about on the stack level, now system means if you are also including balance of plant other things, then the weight, power density and specific density can come down from that 3, or it comes down to 640 watt per liter. So this is if you include your reactant gas delivery system and all other things. Now let us put this thing in bar chart, spider chart. You can see how it looks like. What are the important parameters? The power density, specific power from time, and then life. Efficiency is not that important for even what is being achieved is all right. Other one is the cost, which is very important. And if you are talking about the storage point of view, so this is a cycle, what is being targeted, or the ultimate. These are the same table I am putting in spider chart, and I'm trying to show you, and the cost and other thing. Now let us, will be only, because I'm having expertise mainly in the fuel cell and we are talking on fuel cell, and we only restricting next of the discussion on fuel cell, not on the hydrogen storage. So if you see, already I have shown this same schematic diagram where these are the different components what we have. The membrane electrode assembly is this here, then gasket is there, gas diffusion layer, bipolar plate, end plate. Now, if you talk about then there is also another design factor, like how you make your flow field design, what are the different types of flow field, the channel design, or your humidification design. These things also we call it a design factor. Now, if you talk about the challenges, then these are the components. Like membrane electrode assembly is mainly contributes to the cost and durability of the system. Because if your catalyst is not working good, immediately your performance will be coming down. So fuel cell will be coming to the end of its life. Then design factor also talks about the durability, that if you have good design, you'll be able to make an uniform performance, and if you have an uniform performance, you'll be having good life. Now, if you talk about the bipolar plate, what I was talking about, that 3 mm and also end plate, they mainly contributes to the weight of the fuel cell, because I told that other than that, rest of things are only 110 micron. And finally, if you are talking about the volume, also gasket and GDL layer, also because they are not that much heavy, but they have a good thickness and good volume as well. So they also contribute to the volume. Now let us talk to the cost and who is contributing cost. Let us talk about the membrane. In case of this particular system, Nafion is being used, and I have taken a ballpark number $200 US per square meter. It can vary. Please do not quote this number to anybody. This is a number that I have got this particular quote, so I'm using this one. So you can see that for 1 kilowatt you can get $40 US unit. Only that's a membrane cost. Keep it in mind that the target cost is $30 per kilowatt for the fuel cell stack. Against that, we need now at present situation $40 US for the membrane. Catalyst cost is, even if you calculate in the same manner, you will be getting $60 US per kilowatt. So membrane and electrode itself, its catalyst itself gives you $100 US per kilowatt. And then we can also tell that membrane, if you talk about, we use a membrane, it's called Nafion. The backbone is Teflon. What is being widely used in all these non-cooking utensils, non-stick utensils, and they are damn cheap. So if that's the case, then it is also possible to reduce the cost for Nafion membrane and from $200 to $20. And then in that case, this will be also have an order of magnitude cost, because it is the only proprietary cost, it's not the material cost. On the other hand, if you are talking about the catalyst, the cost mainly comes from the platinum, and the cost, it is impossible to reduce this cost. Even with the mass production, it can go up because of the problem with the demand supply. And this is the, again, this is the target. What you can see here, that membrane catalyst cost should be, it should be targeted is a 3 against, here you can see it is 3 against it is 60. If you talk about membrane, it is 3 against it is 40. So you can see that there's a huge scope for improvement and also reducing the cost so that it can be commercialized. The next one comes is that the bipolar plate challenges. Now, bipolar plate challenges, as you have seen already, that it mainly contributes to the weight and volume. So at present, graphite based is being used, and 3 mm is the thickness. That's an optimum thickness. You can go up to 2.5, but not less than that. And if you see the total cost comes out of it, this is my number again, $140 US. That's what I pay for 300 square centimeter. And it is around 140. You are getting $1,000 US only for the bipolar plate for 1 kilowatt. And then if you go for alternative solution, what is that? Yes, there is an alternative solution. Instead of going for graphite, you should go for metallic base. And it's very easy, because for graphite, you have to machine. I think it becomes expensive. So channel you can do by hydroforming, the stamping or hydroforming, and then cost can be reduced to $3 US per plate for 300 square centimeter compared to that one, and which can give you around for kilowatt $20 US, which is, and you can see that membrane, if you are talking about bipolar plate, is also having a target of around 6 or then $3 US. That's a target. So which we can come now. We can see there is a possibility by mass production, this can come down easily. And these are some examples of metallic. This is the graphite plate. What you can see here. This is being taken from Fosun Center in English, where I worked earlier. And then these are the metallic plate what they have made, and it is in the range, I think, around 0.15 mm thick metallic plate. So this can be, this can help in the reducing the weight of the system. So is that really the platinum is the culprit? That's what I want to discuss in next few slides. And generally, all the people, they say that if fuel cell is so good, why it's not coming in the market? So one answer is that, first answer is that the cost, second cost, third cost is only the cost. And then now, if somebody asks that where from this cost is coming, as you know now, it is coming from the platinum. So, but so I want to actually beg to differ, and in lots of the places I have also told the same opinion. People sometimes think probably I'm talking nonsense. Sometimes people think that I'm talking out of the box. So let us discuss that one. So this is coming from the Indian culture, where if you are going in some places, they say, okay, you try to invest some money in gold and buy some gold coin, and put it in locker. If that's the case, I started my thinking, or my thought process started from there, from a bank where somebody was telling me this one. Then I thought, if that's the case, why it's not true in case of platinum when I'm using in fuel cell? Because we should remember that the platinum what is being used, the maximum portion of that platinum can be recovered because it's a catalyst. It does not take part, it remains as it is. So if you see the research, what it says that you can see that you can get only platinum will be lost around 1% during the entire 5,000 operating hours, and you will be having almost 99% of the platinum available to you. And if you try to recover that, and again you try to make a fuel cell, and all these costs if you include, ultimately it says that you will be having a 13 to 20% total loss in the lifetime. So you will be able to get around 80 to 87% of the platinum back at the end of the lifetime. So it's not a lead acid battery. When you are buying, you are paying, let's say, a few thousand, and when you are going, you are getting few hundred. It's not the case for fuel cell when you are using platinum at the end of the lifetime. And now I did some calculation based on that, taking and tried to find out the salvage value, taking the cost of the platinum and at different time when you are doing. So this is a scenario what I took. So there are two things. One is that optimistic scenario. So scenario one is that pessimistic, where I'm using $32 per kilowatt. This is for 1 kilowatt, $32 platinum. On the other side, I'm using only $3 in the scenario two, which most of the people suggest that we have to reduce the cost of platinum. So I did the calculation. You can see this is how it looks like for scenario one. I'm taking platinum almost 31% as a cost. And if I go for scenario two, where I have platinum is a 5% as a cost, and then if I do some calculation, now I'm going a little fast here because I have only 6 minutes left probably. So if I go by this, so this is I did the calculation for that. I found that the cost of the platinum from 2099 December, how it varied internationally, and after 5 years I found how the cost was. So it was an 18% per annum. That's the cost increase here. This is at the after 10 years, and this is after 15 years how it looks like. So I have done till Jan 2015, and taking this data, I did all these calculations based on those equations, taking 5-year life, and then I took this platinum in person of 18% and took different country or different economic zones like USA, UK, India, Germany, and then other places. And I found that the salvage value what you get for scenario one, which is an pessimistic one, you get almost $61 at the end of the life, and your net, you have already $102 you have. So you have net present cost that what you are paying is actually $42 in this case, not 102. So this is how it looks like after 5 years if you are having the end of the lifetime. If you are going for the scenario two, then the platinum, as you have very less platinum, the platinum salvage value only 6, and your net value, present value becomes 51. So if you see that if you have higher platinum loading, and if you are able to recover that, then you'll be able to get good. And then the next one, if you take now I'm going little first, if you take the next scenario after 10 years, if you are recovering, you'll be getting 221 US dollar as an against 102. So you get also some return out of it instead of doing the losing it. But if you go for the optimistic one, what we are talking about, then you'll be having net $35, and that's how. Now, if you are talking about 15 years, so same thing we can get how we are going. What I want to tell by this is that now if you are using fuel cell in a vehicle, so there you have two options. One option is that when you are talking about platinum that you are using, it's something like, and you know this is a market, okay, we are talking about. So it's like gambling, like a racing. You have a horse, which is fuel cell based electric vehicle, and you may earn money out of it at the end of the lifetime. At the same time, you can also use this particular vehicle to go into the market and do your shopping as well, or doing your daily work. So that's how I see when you are talking about electric fuel cell based electric vehicle, that platinum is not culprit. We should not consider as a culprit if there is an appropriate business model available. Now let us talk about the thematic R&D areas from Indian point of view. If we are talking, so what are the things we need to work? So one is that fuel cell stack. So mainly the development of fuel cell stack with high volumetric and gravimetric power density. This is very important. So that means we need to work mainly on the bipolar plate side, which is very easy. We can do here. And next one is that hydrogen storage system. So there are lots of expertise available here for making type 4 hydrogen cylinder, which can sustain up to 700 bar. Also, we can work on lots of people that are working on metal hydride storage. Very important balance of plant. We need to work on it. And already Tata Motors, they have already developed that balance of plant while they have made the fuel cell bus. And finally, system integration and demonstration. This is very important, and we are lacking in all over the world, everywhere. There are lots of demonstration projects. In India, we have hardly one that is run by Tata Motors for fuel cell, and then other one is with IOCL in, but they are struggling a lot. Whatever I have heard, because even getting this particular vehicle registered itself a big challenge. Now, if we talk about the thematic areas, the fuel cell stack, if you talk, so mainly this is the fuel cell stack. The fuel cell stack performance. So we sometimes what happens that when you are talking about the stack performance or stack testing, always we think that we have to buy fuel cell test station from somewhere, which is very expensive sometimes. Even nowadays I know how to make a fuel cell test station very easily, and then with the help of other people. And earlier I had an imported one, and it was very difficult. When one sensor goes wrong, we have to call them, and they will be telling, will be charging you $4,000 for sending a person. And it's not a rocket science that we cannot do it. So I think fuel cell, we have a huge opportunity for this diagnostic and performance analysis tools. Then other one is that clamping system is very important. Sometimes we neglect this when you are making a stack. Gasket optimization, this is very important, because most of the time we are very much concerned about that, what I was talking about, that membrane or electrode or catalyst, but we always forget gasket. But this is one of the crucial of component when you are scaling up from the lab scale to the scaled up version. And then bipolar plate design and materials, that is very important, mainly when you are talking about the metallic bipolar plate. Hydrogen storage, of course, the testing facilities are not there, so we need to have. There are some laboratories they are now creating for high pressure tank. And then after that, that hydrogen system, hydrogen supply system, thermal management system, and air system for the balance of plant. These are the major thematic areas where we can work in India. Then, so overall, I would like to conclude. I hope I could maintain my time of 45 minutes. High cost of platinum should not be blamed. It's a, if there's a proper business model is available, if somebody is coming and then it will be very cheap, and then it will be very easy to penetrate in the market for fuel cell. There are some other things which I skipped, so I did not give, so that's why yellow portion you forget. And one of the major things that we can, in case of fuel cell, if you want to think about the automobile sector, so we need to reduce the weight and volume. So metallic bipolar plate is one of the alternative solutions, and which will be also having for mass production. It is easy, so we should try for that one. And I think I would be stopping here, and I'll take some of the questions from the audience, or I think that's all from my side, and thank you for your attention. Thank you, Savani.
Thank you so much, sir. It was brilliant, and you catered to all the sections of the participants, like people who did not know about fuel cells at all. Even they understood it, and obviously you took it to a much complex level, which is amazing. Now I hope the audience has some bit of a clue, which and in case you want to research further on it, we can still talk about it. Like, you can write to me and we can discuss further. So without me wasting much time, I would like to take the questions from the audience. So let's see how much we can in this given short span of time. So, so taking question number one is, a person asks here is, what is the most important challenge of implementing fuel cell technologies in India at the moment? So if we have to implement it at the moment right now, so what is the current maturity level? And if we have to implement it, then what are the limitations of putting it on larger scale?
Okay, Savani, thanks for the question. So I think I was talking about one thing, that what is it that it's not coming in the market? Okay, where is the hurdle? And then my first answer is cost, not mine, lots of people. Second, third is only the cost. Okay, so and already I answered that. Probably I'll be disagreeing with that one, and probably audience also will be, some of them, at least Indian people, will be probably agreeing. Yes, we can go for fuel cell, and there is no problem if we can recover 80 to 90% of the platinum, and it might be also giving a business. So then if cost is not an issue, then what are the issues? So recently I was attending another conclave which was organized by DST on fuel cell and hydrogen only. This was only last month, not last month, I think 20 days back. It was in ISA Trivandrum. And there the same thing was discussion. It was coming out that one of the major problem why it's not going to come, or even I'm thinking, I have made a small scooter here, which is probably I'll be uploading my video in another. We were supposed to upload the video last week, but because of the present situation, we could not upload. So we have a 600 watts fuel cell stack, and then we have all other things. Now the problem what happens that if you have this fuel cell based vehicle, where you are going, how will you be refueling it? So one of the major problem is that the refueling station, so the infrastructure of hydrogen refueling station is really limited in our country. It is only one, that is in Delhi, Dwarka. If you have a vehicle here, you have to take it in, you have to tow your vehicle and then go and then refill, and you have to come back and then again you have to try. This is a situation. But I think even I also disagree with that one. I never tell that, okay, that first infrastructure should come, then fuel cell will be coming. And because these people also start talking about that chicken and egg problem, that first infrastructure should come, and then after that fuel cells will be coming, or first fuel cells should come, then infrastructure will be coming. I feel this will be a marriage. Like in a marriage, it's not that bride is coming or groom is coming. You need bride and groom, both of them together, for a successful marriage. So similarly, I think we should have the fuel cell technology as well as the infrastructure. They should be coming hands in hands, and it should happen parallelly. Then only we'll be having this particular system is going to work. This is one of the important thing. Other very important thing is that public awareness. When I run, I'm from IIT Bombay, and we feel that this is one of the prestigious institute. When I am taking this particular our scooter, when we are doing a test ride inside campus, there are lots of people, they come because it looks very awkward. Okay, fuel cell is there, somewhere hydrogen pipes are coming out. So they are very much curious to see that what is this test vehicle. And when you are telling, they do not understand, they have no idea about this. So it's very important that ultimately the end users are this public, and they should accept this. So public awareness is completely missing here. So what we need at present is that for public awareness, at least we should have, and government should take this initiative, that we should have lots of the places, key places where people can experience it and they have an idea what is there. Because I'm giving an example, like in Germany now, in Berlin police they have bought two Toyota Mirai car, and they are patrolling everywhere, and people know that now. If you go there, all the people, even laymen, they know. Yes, this is a fuel cell vehicle. This is done by this company, and this is how it's operates. But in our country, even in the reputed institute, also people do not have any idea what is this fuel cell and how it looks like. So I think public awareness is one of the very important things which is required at this point of time for the market penetration. And after that, they will be, because ultimately they are the end user, they are going to use it. So if they do not know about this, they are not going to accept it. So I think this is the first important step that we need to take, so that we can educate the people and we can educate the people about this technology.
Absolutely, sir. I couldn't agree more with you that public awareness is completely missing. It's not only for the fuel cells, which is comparatively a much newer technology, but also we've been struggling to make aware awareness regarding EVs. People are still, in a very nascent stage at the moment. So a linked question to that was that, see, because of unawareness or lack of information at the moment, people tend to have a lot of misinformation also, which sometimes acts as probably, acting as confusions to people. So when these kind of misinformation or no information at all comes, then people have a lot of myths and anxieties reformed in their heads, so which acts as a speed breaker to the adoption of these new kinds of technologies. So one of such myths are that this kind of technology is potentially quite dangerous to handle. So now, just curious if there are any safety guidelines in terms of the production, storage, or say transportation of these products. So even if not any guidelines, what as a layman we should keep in mind while handling these kind of products when they are in the market?
Yes, so I think this is also very important. And when it comes to fuel cell, and when fuel cell comes, it comes automatically hydrogen. Now, there's a myth, or there's a, because all of us we know that there was a disaster known as Hindenburg disaster in the 1937 6th May. And
Yeah.
from that time, people started believing that because it happened because that particular Airbus was destroyed because of hydrogen. After that, it was realized it was not because of the hydrogen. I wanted to tell, because sometimes when you are talking about the fuel cell, and I was also talking in these slides that you will be having a tank of 700 bar. When you write 700 bar, you do not understand what is this. Okay, so it's a huge pressure, because sometimes you will be understanding, let's say if you are having a small air gun where you are putting in and then you are trying to push that air gun with your finger. I tried several times by mistake, and then I used to realize that, okay, how that pressure means there's hardly 1.2 bar still. So now when you are talking about 700 bar, it's a huge pressure. And then people start talking about that whether it's safe. I have to tell some of the things that which looks like myth, or when it comes to hydrogen, because of that disaster, people takes it separately. Now, if you talk about, let's say, I will be talking about our LPG gas and hydrogen. Let's say I have a LPG tank, or also I have a hydrogen tank, and we want to now shift from the fossil fuel based technology to the economy to the hydrogen economy. So my kitchen is having hydrogen tank. Now, let us take there is a leakage in case of hydrogen as well as in case of LPG. In case of LPG, as it is heavier than the air, if it leaks, it will be actually settling on the floor. If you take hydrogen, it is going to actually settle on the ceiling, because it's very light. Now, if it catches fire, at least you can run through the door. But if you take an LPG gas, you will be running over the fire. So these are some of the things, but day night we are actually using LPG and we do not feel that much of. So it's only thing that when you start using it, then we'll be feeling yes. And if we know what are the methods how to handle it, then there is no problem at all. Other thing, now 700 bar, I had an opportunity to visit a lab in Vancouver who does all this certificating, and then so they were showing me one after another that how this particular cylinder is safe. So they are telling that they have different types of testing. So one is that if you fire a bullet on this particular tank, even that bullet cannot penetrate, it comes back. And they are showing me the video. They told we cannot show you now the live, but we can show you the video. So I saw the video that they are firing a bullet and how it is actually rebounding and it's coming back. And if then there is they have a test that they throw this particular 700 bar tank type 4 from 6-story building, I think, or 4-story or 6-story building, and it jumps like a football. Nothing happens. So because of that high pressure inside, because of all this, if you are using electric vehicle, there is not going to be any problem, any safety problem. And as also other thing, we know that hydrogen is having very, if you talk about the total energy content, it's having very less energy content in some terms of volume. In terms of weight, it shows, but always when it's leaking, it's going to be in terms of volume that you will be having. So That way it is not that much dangerous as people think. But of course it has to be handled properly, otherwise we know that we had a disaster happened in a premier institute like Indian Institute of Science in Bangalore in handling hydrogen. Similarly, after that, after 2 months, it happened in IIT Bombay also, where people were also handling hydrogen. So there has to be some protocol, and people have to follow this protocol. Then it's not unsafe.
Right, absolutely. So next question is that imagine in a utopian scenario, in a hypothetical saying, that the government announces that, okay, from now on, all, the vehicles, older or new, are free to do the transition from current fuel technologies, which also includes EVs, to these new forms of technologies. Okay, so now, as per your experience or your point of view, which do you think should be the first segments of the transport sector to go and adopt these kind of technologies? By segments, I mean two-wheelers, three-wheelers, four-wheelers, or buses. And why should they adopt it in the first place? Secondly, once you choose the mode, if you could tell us from the cost aspect, if why does it make sense for them to adopt this, and how is it different from current ICE technologies or the electric vehicles or even the hybrid ones? So that's the question, sir.
Okay, so this is, I think, if you talk about fuel cell, it's very difficult at this point of time to penetrate, but still, when government is going to around, they are not talking about the cost, I hope. So in that case, we are ignoring the cost part, then we are discussing this particular thing. So I'll be assuming that the best option will be a three-wheelers, where in our country, like auto, we call it. And other than auto, also two-wheelers would have been good, but the main problem with two-wheelers, accommodating the fuel cell tank and fuel cell becomes very difficult, because I have faced this as I was making the fuel cell. We have already converted that electric vehicle. We bought an off-the-shelf battery operated scooter, and then we converted it to fuel cell hydrogen based scooter. It looks very elegant now, but we had really tough time to fit that one. So that's what I'll not be suggesting two-wheelers for the like Activa and other thing, but if you go for the other types of the vehicles, two-wheeler vehicles where you got a motorcycle type of thing, there you'll be having some space where you can mount the fuel cell. So best option would be the public transport, and it is auto or the public buses in the cities. Why I'm saying this, because as I was telling that we always tell that there's a chicken and egg problem. So instead of that, for having a good, it's good to have marriage. It's better to have both of them should be existing, and they should be having in a high population. So if you take in some let's say cities or some metropolitan cities, let's say, so there you can create this infrastructure very easily, and where utilization rate will be more compared to the other places, and then you can use for the public. At the same time, it will be also helping for the public awareness, and slowly people will be. So but if you talk about auto also, it will be an individual who is going to own it. I think it's going to be very difficult at this point of time if you talk about an individual is owning this one. So from that point of view, it should be some government or private public buses owned by the government, and then they can operate it. That could be the first stage. And if you are talking about auto also, now if it goes from that government to, if individual wants to own it, then it should not be in the beginning. It should be like now we have an electric vehicle operated by battery. Then the next stage will be is an hybrid battery and fuel cell, where fuel cell will be giving you the average power and battery will be used when you need high power, and so that you can reduce the size of the battery for your electric vehicle, and total cost can come down, or you can cut down the cost. And finally, when there is a business model is available and cost is not there for platinum and all other things, then somebody can own. At that time, it will be the first auto can be the three-wheeler could be the first thing what I feel.
Brilliant. So I'm afraid I can take only last two questions, and the second last one is, so if we link it, these new technologies with renewables, so how feasible is to compare it with the EVs or the ICE vehicles at the moment from techno-economic point of view, if we have to commercialize it, and by when can we expect it to see it on ground in Indian scenarios? And I mean, like, by comparison, I mean, like, is it also feasible to compare it? Because too much comparison sometimes doesn't make sense. So how feasible is it to, compare renewable energy linked to these new technologies compared to EVs in terms of techno-economic aspects, in terms of wide scale commercialization in Indian aspects?
Yeah, so when you tell this, I remember one particular thing which I'd like to tell. I love playing football. Okay, so that's what I would like to give that example of football. So it's something like that. The small kid is actually now getting trained at the age of, let's say, under 12 he plays, and all of a sudden he's being asked to compete with Sunil Chetri. How it works? This is
Yeah.
what is happening now, because if you see, this is completely, and we always tell that we compete with IC engine, which is almost 200 years old technology. And so that means you are being asked a particular, or somebody who is just running, and then you are telling, okay, you run with Mr. Bolt, okay, for 100 meters. So there you need some support, of course. So, and if you are not getting this support, it's very difficult to compete with. The similar thing is going to happen now when you are talking about, let's say, solar hydrogen, and you are talking about that other fuel cell, fossil fuel based. Fossil fuel based, they are very cheap, and if it comes to the end user, they don't care. Even at least in the context, first it comes to their mind is the cost, and if it is expensive, it will not be accepted. So in that context, solar hydrogen, if you are talking about, is going to be 5 to 6 times expensive compared to the other hydrogen production route, as I was showing there. So if keeping that in mind, so it will not be viable at this point. But of course, with time, if the fossil fuel cost is going to increase, so there will be a trade-off when this will be that fossil fuel cost will also catch up with this one, and that time this will be, so it is not in near term, probably in mid-term or long term, it's going to be the ultimate solution for hydrogen. But at present, probably it is not a viable solution for this one. But of course, there is another thing for at least for the automobile sector. But if you are talking solar hydrogen, we can also deviate a little bit from in the discussion. Probably for stationary applications, solar hydrogen can make some difference, because hydrogen storage has some of the quality which is not having in the batteries. So hydrogen you can store for season, what you cannot do in batteries. Now, if you go for a particular stationary application where you need to store in the summer, and then you can use in winter because your battery is getting discharged. Let's say every day you have foggy day and this type of thing in solar system. That time hydrogen comes in picture along with battery. So always they are complementary, they are not competitor. So in that context, if it comes in case of stationary application, there is some opportunity, of course, at present as well, because you can improve the reliability of the system if you are adding hydrogen along with the battery, which is very difficult if you want to do only with battery. So in that context only, I'll be telling at this point of time, probably it will be almost 6 times cost compared to the conventional hydrogen production route. So if somebody wants to is willing to afford, then there is no problem. Otherwise, it is not an economic solution at this point.
Absolutely. So that brings us to the last question. So you have been involved in this kind of research since so many years now. So from your experience, I just want to address a set of questions that addresses to certain part of our participants, which are the manufacturers and the investors. So probably they would be really worried about, what is going to happen to us who has already invested in the EV sector, or the ones who are potentially willing to invest in new forms of technology such as this. So what would be your advice to them who are in the planning stage in terms of investment and planning, for them to save a lot of time on, miserably failing, trying on testing some things that that don't really work and that would save up their time and money. So what would you advise them? Which are the sectors that it is worth, discovering in terms of obviously fuel cells? And what would your recommendations be for them?
Now, if you take this particular question a little bit tricky, because when you are talking about, let's say in our country, people are working already in the electric vehicle. I'm not sure that how many people are actually working on the batteries. Now, when you are talking about now electric vehicle, fuel cell based electric vehicle and battery based electric vehicle, rest of the things remain same. So like I have bought this particular scooter, I removed the lithium ion battery and then I put my fuel cell and I tried to accommodate my fuel cell and hydrogen there. So if somebody is working on battery, then there is no, because you cannot use that particular system for fuel cell. But rest of the things, it will be of course useful, and you can, it's like a plug-in, you can always plug in a fuel cell as well, or you can also plug in fuel cell and battery together. That's what we have done in our system. So now if you go for fuel cell, if somebody wants to invest, as I was showing, there are different things which we can invest, like membrane is already, we are also importing. There is not that much of success in getting our membrane made here. Catalyst is also it's a precious metal catalyst. So whether you are making here or there, it doesn't make any sense because the cost is coming from the material itself. Now, third one, what is that the metallic plate? What we are talking about? It is really, I tried my level best to get a person who can make it for me, and I did almost 3 to 4 months of research, and nobody came up to make it. So, and finally I found a person who is making for me, and we have actually in next I think 1 or 2 months we'll be having our fuel cell ready with metallic plate, and we have gone to advanced state. And just I want to tell you one of the application what we are trying, like it's an electric vehicle, but it's a drone. So we are thinking of taking it, we are trying to put a fuel cell in a drone which can take weight up to 20 kg. That is our first target, and that is, there are lots of applications in the army, because sometimes there are lots of places in the hilly area. I work with the army in some of the hilly mountain area, and I find that they say that lots of the time they have difficulties in sending the ration. And if you have a drone which you can send it, because if you take an aerial distance, it will be hardly 5 minutes, but you will be requiring 4 hours when you are traveling by vehicle. So, and we are now in that process of making this particular system, and we are making the fuel cell and metallic bipolar plate, which is one of the very important thing we should work on. Other thing is that testing devices and testing protocol. Another thing, that is what we can do here very easily, which we are not doing. And here also lots of people, my other colleagues, and when they are initiating their research, first thing they tell that they want to buy a fuel cell test station, which costs how much? 1 crore. And without that they cannot do anything. And then that can be done very easily if you are buying some of the components, and then you can do it. Those other things can be done very easily. So diagnostic tools and other things can be made very easily. People should try. And for fuel cell stack, mostly things are available in the market, like membrane and catalyst is available in the market. So we cannot do anything. It's only bipolar plate and that thing, and design we can do here, and we can do the balance of plant very easily. So those are the things we should concentrate mostly.
Absolutely. So this brings us to the end of the webinar. So my personal experience of attending the webinar was an absolutely eye-opener, and I have a different aspect of looking at things just now. I would like to, thank Professor Ghosh for making it super easy for us, because I understand one slide could actually, take up one lecture for this, because the thing is so complicated. If you want to go deeper on the subject, of course, but he has beautifully explained to us in a very simple manner, and well set between the time frame. We were also able to take a lot of questions from the audience. So really, Professor Ghosh, thank you so much for your time. And I know it was really difficult in such times of crisis, but you still made it. It was wonderful. Thank you, audience, that you without fail attended my webinar, and you've always been doing it. So I hope to see you next month as well. In that span of time, if you have any interesting topic which you would like to see from us, presenting next week, please write to me at shravani.sharma.org. We have received a lot of questions. I'll be sending it to Professor Ghosh and we'll see how to address it, and we'll be uploading it in the same link. And good news is in 1 week or so, you'll be getting a notification where we'll be having the presentation as well as the video in the same link. I couldn't complete this webinar without thanking our funders, the Shakti Sustainable Energy Foundation, without whose support this wouldn't have been possible. So signing off for today. And before that, any last words from you, Professor Ghosh, before I end this off?
No, it was a wonderful experience for me as well, Savani, and I would like to thank you. And also, once again, I would like to thank your organization for giving me this opportunity and sharing my views. Of course, it was in 45 minutes and talking about fuel cell sometimes becomes very difficult. Sometimes I'm talking fuel cell entirely for 1 semester here. So sometimes putting an entire thing in 45 minutes, even I also don't know which one I should not tell, and it becomes very difficult. But thank you very much, and it was really wonderful interacting with you, and I hope that audience liked it. And if they have any problem, any question, they can always also reach me out. So thank you.
Brilliant. Thank you so much. Cheers. Bye, audience. Stay safe. See you next month.
Bye bye.